last little piece where I want to connect this to the minorization problem. So I have a function f of theta, which is defined as the likelihood of x given theta. That's one function. The other function I'm defining is L of q theta, which is defined as the expected value under q of the log of p of xy given theta divided by q of y. This is the function LQ theta, and what we know from this analysis is that L of q theta is less than equal to f of theta. Now this is not quite exactly the problem that we are after, because in the minorization idea, the q and the theta live sort of in the same space. We are living, the q and theta live in the same space. In this particular case, theta is a parameter, q is a distribution, so they don't exactly live in the same space. So that's why I'm saying that EM is not minorization directly, but it's a variation. But what I want to be able to show is that if you give me a value of theta, there exists some q theta such that this is exactly equal to f theta. Can you, looking at this expression, tell me what q theta is going to be? That there is a distribution q theta such that if I plug that value of q theta in there, I get exactly f of theta. Then it sort of starts to look like minorization. I've got a family of functions in two variables, q and theta. No matter what value of q it is, this will turn out to be less. But there is a particular value of q, which is, let me call that q theta, for which they are both equal. Given all the analysis that we have done today, what do you think is that q theta? What is q theta? What will be the distribution that will make things equal? What is your guess? Well, remember, what is q? It's the distribution of y. So what will be the distribution of y which will make everything work out correctly? Sorry? No uniform? No, then I have no information. That's not going to work. Why should Gaussian come into the picture? I have to make everything equal. So look at this expression. What should I plug in here so that I get that back? Right? Because f of theta is log px given theta. What should I plug here for q such that I get that back? Theta is not a distribution. Q of so q should be a distribution of y, and such that if I plug that value here, I'll get back that expression. So what is the distribution of q that we have been playing with? What is our best distribution for q so far? What is that? No, not normal, not Gaussian. This is equal to the probability of y given x and theta. That's what we've been looking at all the time. Q theta of y. I mean, I don't know whether the q of y that we've been looking at, q star of y, the optimum value is exactly that. It's the posterior distribution of y given my data and the parameter theta. So let's plug that in and see what happens. So if I plug that value in, if I look at p of x, y given theta and divide by p of y given x theta. So this is the numerator over there. This is the denominator that I'm guessing is the right answer. So if I plug that, put that in the numerator, I can write that as probability of x given theta, probability of y x theta divided by the probability of y x theta. These cancel. You get inside the bracket inside in here or over there, it doesn't really matter, over here let's say, in that bracket you get P of x given theta, because the other components just cancel out. So this ratio just becomes the probability of x given theta. So this is a constant that doesn't depend on y, it gets outside. What happens to this expectation? It just gives me 1. So because this is a constant, it gets out, this expectation gives me 1, and so I exactly get the quantity that I'm after. So what's the punchline here? If I define these two functions, I get that L of q theta is less than equal to f theta. Optimizing this in q and theta is easy. If I fix q, I can optimize in theta. If I fix theta, I can optimize in q. And I have a value of q theta which is exactly equal to f theta. You give me a theta, I can find you some value q theta where these quantities are exactly equal. And that particular value, q of theta is of y, is nothing but the probability of y given x and theta. So give me the value of theta, I get you this. And that is the connection that EM has to minorization. And we will see that we will exploit this idea later on in trying to do other things. Okay, so now comes the part where I have to ask you to do things. So the first homework problem that you have, and this one I have not assigned, so you should write it down, is I want you to write a function which is equivalent to that function. So you have this workbook with you, you have this function there. This is the function when the coin identity is known. When the coin identity is known, I'm optimizing that negative likelihood. What I want you to do is transform it into another function where the coin identity is latent. It should look something like this. This is the correct solution. But I want you to work that out for yourself, and we will go over it in class tomorrow for a little bit to see where you are there. The other thing, so that's one homework. I'm not going to click on it because you will see the solutions. The solutions are there, so please don't look at the solutions, just do the assignment. So I want you to do those assignments, and then I want you to do this one coding example so that you'll get some idea of what's going on. For those of you who are more invested into Python, one of the things that you could do is you can write a code to actually generate that. The first example actually has a way to, you can write a Python code that will solve the problem for this one. It's a very simple Python code that you can try doing it. I just want to make sure that before you leave this, you have done something by hand so that you know or are comfortable doing it. So it's not going to be very complicated. Try the Python code for problem 1. I don't think that I have posted the solution for problem 1, thankfully. And the last one is also actually very interesting. For those of you who have seen a random effect model, you have a situation where the jth observation of the ith subject is given by a random effect model. This is something that is done all the time, that you have something which is class based and something else which is individual based, and this will tell you how to write various things. And tomorrow in class we will spend a little bit of time going over this, going over the solutions so you have an idea. So make sure that you do this before tomorrow morning, or maybe let's see how far you go. Definitely do the problem for that small Python example, do problem 1, and then think about problem 2 and 3, and then we will see where we are on that. All right, very good. Now we're going to switch gears and go to the next module, which is thinking about support vector machines. And then we'll go to the other one. No, I don't want this one. All right. So support vector machines and the kernel trick. This is another pretty hot topic on various kinds of things, particularly the kernel trick. And we will try to see how we get there. This time around, when you do as you will see in the slides, we are getting away from probability theory and starting to look a little bit more about optimization, geometry, classification, and so on. This is the overall story, but we will let's just dive in. Okay. So support vector machines are non-probabilistic binary linear classifiers. Binary meaning there are two classes, 0 or 1, and we want to classify between these two classes. Later on we'll see how that can be extended to multiple classes, but the extension to multiple classes tends to be very ad hoc. It's not very clear how to do, and we'll talk about it. We will talk about something called basis functions in the kernel trick, which makes SVM a non-linear classifier. So basically the idea is that you have at its operations, support vector machines are linear classifiers, but if you want to make them non-linear, the way to do it is to raise the data point into a higher dimensional space and then make things non-linear over there. We will see how that works. And in practice, support vector machines are very popular because of this kernel trick. Without the kernel trick, support vector machines are not going to be very powerful machines. Later on, the name that comes support vector machines, this name support vector comes from the fact that if you do the classification, there are very few data points which are called support vectors that support the decision making. Those are the points that determine what the classifier looks like. Very few of them, and we will talk about how that works as we go along. They are very popular classifiers. They are used for text classification, outlier detection, phase detection, database. There should have been a comma there. Databases, marketing, and many others. They're also used for multi-class classification. There's also support vector regression, and we're going to cover all of this in this module. So let's start with a very basic idea. Suppose there are two classes. For now, let's assume they're linearly separable. What does linearly separable means? It means that, it means basically there are these two classes, the magenta dots and the yellow dots, and there exist lines, a linear separator meaning in two dimensions. It means that there exists a line that separates the yellow dots from the blue dots. What I'm looking for is a set of lines that separates them the most possible. I'm looking for a solution where I will tilt these lines in such a way that the separation between the closest yellow class dot and the closest magenta class dots is the maximum possible. Okay, that's the question. Sorry? I don't understand your question. Closest to each other. Because there is a yellow class, there is a magenta class. We want to make sure that the closest point here and the closest point there, meaning their linear separation, is the maximum possible. Okay. All right. So now my data points come with labels. In order to make things a little bit easier later on notationally, I'm going to say that a point is xi and the label is ti. Ti takes values -1 or +1. Okay, it could have been 0, 1, it would not have made any difference. I like -1 or +1 because it turns out that later on that makes mathematics a little bit easier. If the label is 0 or 1, you can easily translate it to make it -1 +1. Okay? A linear classifier is of this form. I take a linear vector W transpose X, so this is the inner product between W and X. X here could live in some d-dimensional space. I take the inner product of that and then I add a shift B. And then I take the sign of this. So sign is +1, -1 or 0, but the 0 part I will just include it into the +1. So if the quantity inside is 0 or greater than 0, I'll define that to be +1. If the quantity inside is negative, I'll call that -1. Right? So this is how I separate them. Now one thing to keep in mind is that if I look at this perturbation, if I rescale W and B, if I multiply W by some number, let's make it twice W and B also twice B, it's not going to make any difference to this sign operator. So I can rescale things so that my boundary doesn't change. All right, very good. So I'm going to choose a W and B such that W transpose Xi plus B is greater than equal to 1 for all TIs, for all points I for which the label is equal to +1. If this happens to be less than 1 for any one of them, just rescale it higher. And remember that rescaling it by a positive number is not going to make any difference to this, so I can rescale things. And I'm going to assume that W transpose xi plus b is less than equal to minus 1 for all ti is equal to minus 1. Now why can I say that I can always find this? Because I'm assuming for now that they are linearly separable. There exists something that will separate them, and by rescaling things I can make sure that it's always greater than 1 and always less than 1 for the other one. Alright? Very good. So that's the picture. So these are the points that were there. This side, on this side I want everything to be greater than 1, on this side I want everything to be less than 1. So the perpendicular distance of a point x from the hyperplane W transpose x plus b equals 0, if you go back at least, unless things have changed in the last 25 years, somewhere in 12th grade you would have learned that that's the difference between the two lines. If I give you a straight line W transpose x plus b equals 0, and I give you a point x, the distance of that point x to that perpendicular is given by W transpose x plus b divided by the value or the 2 norm of W. And what is the 2 norm of W? It's each of the components of W squared square root. And so this is what the expression is. So the distance of the closest points to each class of the classifier is 1 over this. Why did I come up with this? Remember, I have assumed that for all the positive class, W transpose x plus b is greater than or equal to 1. For all the negative class, the W transpose x plus b is less than or equal to minus 1. So for the closest point, this quantity is equal to either plus 1 or minus 1. So therefore the distance between them is proportional to 1 over the norm of W. Okay, very good. So what I'm going to do is that a support vector machine, an SVM, seeks the maximum margin classifier that separates all the data. It maximizes the W, or rather it maximizes its difference, which means that it minimizes the norm of W that will make sure that the points are as separated as possible. Why do we care about that? Well, it seems like a good idea, meaning separating points is a good thing, but there is also firm statistical learning theory based methods which say that if I maximize the margin, the out of sample performance of my classifier is going to be very good. So the out of sample performance of a classifier is intimately connected to that margin, and therefore maximizing that margin is a good idea. Okay? Maximizing the margin 1 over the norm is equivalent to minimizing 1/2 of W transpose W. Alright? Very good. So now we end up getting this optimization problem. You want to minimize the objective function f of W, which is 1/2 of W transpose W, subject to the constraint that Ti, the label, times W transpose x plus b is greater than or equal to 1. Now how did that happen? So what does this inequality basically mean? If Ti is equal to 1, it would mean that W transpose x plus b must be greater than or equal to 1. If Ti is equal to minus 1, it would mean that W transpose x plus b is less than or equal to minus 1. So from here, this is the reason I like the Ti's to be plus 1 minus 1 rather than 0 1, because I can write everything into one constraint. Okay, so this is the problem that I want to solve. What kind of an optimization problem is this? Quadratic program. Does everybody see that this is a quadratic program? The objective function is quadratic. The constraints are all linear, because what are the variables, by the way? It's W and B. I'm looking for both W and B. So the constraints are all linear in W and B. The objective function is quadratic in W and B. Therefore this is a quadratic program. Can we say that this problem is convex? Is this a convex optimization problem? Yes, no, maybe? Yes. Why is it so? The constraints are linear, so I don't have to worry about them. What about the objective function? It's a convex function. What is the Hessian of the objective function? What is the Hessian of this objective function? What actually is the Hessian? No, I'm not talking about gradient. I'm talking about the Hessian matrix. No. Tell me the actual value. Don't tell me that it's positive semi-definite. This is a function of W. What is the Hessian? Come on guys, you should be able to do this. Wi? This is quadratic. If you take a second derivative of a quadratic, it has to be a constant. So what is it? I. Identity matrix. Good. So this is a quadratic function. You take its second if its gradient is going to be w, because this half will cancel off the 2w, its second derivative will be identity. Perfect. Good. And identity clearly is a positive semi-definite matrix. In fact, it's a positive definite matrix. Fine. So this is a great optimization problem, very simple to solve. Now the problem is that in reality, n could be in hundreds of thousands. Even in a small little problem, the number of data points that you have are in hundreds of thousands. The x, we now want to use support vector machines for all kinds of things. I'll show you a support vector machine example later on, which is for classifying faces. So faces, let's say that it's grayscale. So it's it's a vector, some number between 0. Every pixel is a number between 0 and 1. And let's say it's 256 by 256. That's a pretty reasonable sized image. Or maybe make our lives a little bit more complicated, because what is 256 squared? It's like 1,000,000 divided by 16, whatever that is, some reasonably large number. So the dimension of W is 256 by 256, because xi's, which are the images, are of that order. So if I want to take the inner product between these two objects, this is going to be a high dimensional object. The number of images is large. So this quadratic program, even though it looks very nice, ends up becoming a fairly complicated object. Towards the end of this module, I'll tell you how people solve it nowadays. They don't solve it this way, they solve it a slightly different way. Okay. Back in the day when people started solving these SVMs, they did not have the modern technology that is available to us right now, and they still wanted to solve this problem. And the way they got at it is to not to solve the primal, but to solve the dual. And dual becomes easier, and it opens up some other geometrical features which are worth keeping in track. So this problem, primal problem, is a convex quadratic program. Moreover, the objective is strongly convex. The strong convexity comes from the fact that the Hessian is positive definite. It will have a unique minimum. Only the points closest to the boundary define the optimal hyperplane. That's the picture that we already saw. These are support vectors. And we will see that the solution can always be represented using these points. We will go to the dual to fully understand SVMs, and then use something called a kernel trick, which is extremely important for SVMs. So here's what we're going to do. In order to construct the dual problem, I'm going to construct a Lagrangian. And the way we construct the Lagrangian is we take the objective function, we multiply, these are all the constraints that I had, Ti, W transpose X plus B minus 1, alpha I are the dual multipliers. I'm going to restrict that the dual multipliers are greater than or equal to 0, and I'll construct this Lagrangian. Now, and then I'm going to take the minimum. Okay, hopefully this is not going to die on me. I'll fix the value of alpha and take the minimum of this Lagrangian over all W and B for a fixed alpha. And my claim is that G alpha is less than or equal to FW for all feasible W. How do we show that? That is, this dual function value is actually a lower bound on this quantity for all feasible W's. How do I argue that that is the case? It's not too important for us right now, but if I end up needing it, I'll come back to it. So, but this is true, that G of alpha, for any value of alpha greater than or equal to 0, G of alpha is less than or equal to F of W, which is 1/2 W transpose W for all W that are feasible. We'll come to it. If not, we'll check it, and if I don't need it, just take it as a given. The dual optimization problem is going to be the maximum of G of alpha for all alpha greater than or equal to 0. Since the primal problem is convex, it follows that the primal value equals the dual value. That is, G alpha star is equal to FW star, where alpha star is the optimal solution of the dual and W star is the optimal solution of the primal. This is what is called a strong duality, and we'll be using the strong duality later on. So in order to solve this dual problem, in order to set it up and solve it, we have to start from the Lagrangian, minimize that over W and B to find out the expression, find the value of G alpha, put it back here, and then see what happens. We will do it one way this way, and then when we get to another problem later, I'll show you a different way of doing it, which uses some ideas from game theory and from saddle point problems, and turns out that calculating things that way becomes easier. And the homework problem that goes with this module, you will do, I'll force you to do it that way so that you have a better idea of what happens. Okay. So let's take the partial derivative of L with respect to B. You will get this expression, alpha I Ti must be equal to 0. Where do you get that from? If you look at this expression, take the derivative with respect to B, the coefficient of B is alpha I Ti. You take the derivative with respect to B, this disappears, and you just have sum of alpha I Ti must be equal to 0. What happens from W? If you take the derivative of this with respect to W, from here you'll get W as the gradient. From this one, you will get alpha I Ti Xi. So because this expression can be written as the sum of alpha I Ti Xi transpose W instead of W transpose Xi. Take the gradient of this, you'll get alpha I Ti Xi. From here you'll get the gradient W, and that gradient must be equal to 0. Therefore you'll get W must be equal to alpha I Ti Xi. Why? The first order conditions, which is what this is, are necessary and sufficient for optimality. Why? Why is it necessary and sufficient? It's necessary for optimality. Why is it sufficient for optimality? What is the property that I'm using that these conditions are actually sufficient for optimality? You know the answer, so you might as well say it a bit louder. It's necessary because for any optimization problem, in order for this to be a global minimum, it must satisfy this condition. And what makes sure that if I satisfy this condition, this must be globally optimal? Convexity. Because this problem is convex, I can take this first order conditions, and that gives me the answer. So now I have a constraint here that alpha I Ti must be equal to 0. I know what W is, it must be alpha I Ti times Xi. I plug it back in. So from here I get this expression alpha I, what is going on here? Basically because I take W transpose W, so I get a pair of terms alpha I Ti Xi, alpha J Tj Xj. That's what is going on over here. Alpha I Ti Xi transpose alpha J Tj Xj. And there's a summation of ij going from 1 through n, 1/2 from there. And from here I put I equals 1 through n, alpha I, 1 minus, this is W again, transpose B. If you go through this summation, there's a summation ij over here, there's a summation j over there. From this part you get the summation of the alpha, fine. From this negative part, you will find that this negative part is exactly the same as that without the half. So this half cancels 1/2 of this, and you get a negative of this object. This object is nice. We will see in a moment what's going to happen. So you'll get sum of the alpha i's minus this object. So that's the optimization problem to solve. You want to maximize over alpha, the sum of the alpha i's minus 1/2 of alpha I, alpha j, Ti, Tj, Xi transpose Xj. Sum of alpha I, Ti must be equal to 0. Alpha must be greater than or equal to 0. Why do we like this problem better? This is also a convex quadratic program. Nothing much has changed. It's a convex quadratic program. But it only has a single constraint and single equality constraints. These inequalities of alpha greater than or equal to 0, they are trivial to handle. They are not very complicated constraints. But the only non-trivial constraint is this one, which is the sum of the alpha I, Ti must be equal to 0. And that makes life easy. And that's one of the reasons that people prefer to solve the dual as opposed to the primal. But what has happened in the process, something to keep in mind, is that in the primal, the number of constraints corresponded to the number of data points that you have. In the dual, the number of variables alpha I corresponds to the number of data points that you have. So if you have a lot of data points, the dual will have a lot of variables. But remember, one thing that we've been talking about is many of these alphas will be equal to 0. And therefore, even though you will have a lot of data points, a lot of variables. Many of them will turn out to be 0. So if you are trying to solve this using an active set method, which is the typical solution method used for solving these quadratic programs, many of those variables will be 0, so you don't have to keep them in memory. They will just disappear, and so things are going to be pretty efficient. What was the complementary slackness condition? That's again from the Lagrangian. At the optimal point, since this quantity must equal to the dual, this quantity must be equal to 0. So this complementary slackness says that this quantity must be equal to 0. You can check for yourself that alpha i's are greater than or equal to 0. This quantity inside the bracket is also greater than or equal to 0. So if this summation has to be equal to 0, then individually each of these terms must be equal to 0, which says that alpha I times this quantity in the parenthesis, ti w transpose xi plus b minus 1 must be equal to 0. So alpha I can be non-zero only if this bracket is equal to 0. What does that mean? It means that only for those points that fall exactly on the two hyperplanes is the alpha I is non-zero. They're only going to be non-zero for the points that fall exactly on those hyperplanes. So just to show you a picture, where did it go? Here. So at the optimal point, here's the separator. This point corresponds to w transpose xi plus b equals minus 1. This one corresponds to w transpose x plus b equals plus 1. If you want the alpha to be non-zero, the point must lie on this plane or it must lie on that plane. Now you could have an unlucky situation that all of these guys fall right here and all of those guys fall right there. But in practice, there's enough noise that the number of data points that fall onto these hyperplanes is significantly smaller than the total number of data points that you have. As a result, we know those alphas are going to be sparse, meaning many of them are going to be 0, and that's going to be helpful because then I don't have to incorporate them into that optimization problem. Life becomes a little bit easier there. So if alpha star is the optimal solution to the dual problem, how do I get the w? Remember, by the first order conditions, we have that w is equal to alpha I ti xi. So instead of alpha I, put in the optimum value and you get the answer from there. How do you get b star? Remember, for if alpha I is positive, alpha star I is positive, then the corresponding bracket here must be equal to 0. I know w star already, so I can solve for b. I can solve for this and set it equal to 1. Now here I'm saying that you obtain b star by noting that this must be equal to 1 for any I with alpha star I greater than 0. Pick any I that you like and you get alpha star I equal to 0, positive, and you get that solution. Mathematically this is exact. This is what you would do. Computationally, is this a good idea? From a computational perspective, how would you solve this problem? Would you pick actually this way, or would you do something else? If you were going to solve this problem, you got the value of w and you also have alpha star, would you pick any one where alpha star I is equal to greater than 0 and solve this, or would you do something else? When you do something numerically, always allow for the possibility that things are noisy. So if you have noise, we like to do what? If I have noisy data and I am trying to estimate something from that,
taking alpha I equal to this.
No, I can't do anything with alpha, it's given to me. Somebody has computed that optimal solution alpha and it's given it to me. And now I'm just picking the alpha which is positive, one of those, and doing that. Versus?
Penalty.
Sorry?
You can give penalty for that.
No, what penalty for what?
Do it for multiple points. Do it for multiple points.
Good. Whoever said that, can you elaborate a little bit?
You can do it for all the points with alpha I greater than 0.
Perfect. And then do what? I can't do for all the points, right? Because then I might get slightly different values. So instead, what do I do? If everything was mathematically right, and I want to consider all possible points rather than just one point, what would I be doing in that case? How would I compute the b? Your idea is right. Don't focus on just one alpha. Focus on all the alpha which is positive, and the same B should work. But it may not work because the data is always a little bit noisy. So in that case, what do I pick this B to be?
Take it as close as possible to 1 for all the cases together.
Instead, whenever something is noisy, what do I like to do? The mean or the median. Whatever. So you will have different values of B. Just take the mean of them. That gives you the closest, sort of minimizes the difference between the various errors. Or you take the median if you feel that if there is a big, hopefully the parameter, the variation in B is small, so you don't have to take the median, but we can take the mean. So mathematically this is exact. Numerically, don't do this. Take something from. But like I said in the beginning of these lectures in the morning, when we get down to showing you something on Python, we'll never do this. Python will just give me the answer and I will say that okay, I'll work with it. My whole idea behind this is just to give you, if you're writing something from scratch for an optimization problem that has some complementary slackness type conditions, don't rely on just one of them. Just take an average, it will give you a better answer. If everything is right, the average is going to give you the same answer. But if things are not quite exactly right, the average will give you the better answer. Okay. Now, suppose the data is not separable in X. Oh, now this is going to, let me actually see. I want to see one thing. I don't know whether this is going to work. Maybe I'll have to run the video off of something else. Okay. So in some ways the basic idea behind, now let's not do this. Let me actually come back to this. I want to show you an easier problem first, which is this one, and then I will go back to that other case later on. Suppose now, and this is the part where I wanted to show you how to get some duals very nicely, and the dual for this is this particular function. I want to get to this dual from a different way to give you an idea, and you will do it for a different problem in your homework. That will come not today but tomorrow. All right, so now we want to consider the possibility that the data is not separable. Does everybody have this password? Perfect. So we'll get rid of this. And the reason I want to do this is because it has a nice connection to other kinds of machine learning problems. So I don't want you to think about SVM as being something completely. So let me actually go a little bit further and come back. So one way to think about this problem of SVM is the following. I want to minimize a loss function which is a loss function that depends on Ti W transpose Xi plus B. That's the loss of that data point, plus a regularizer 1 over 2C W transpose W. This is sort of a general penalized classification problem. This is sort of where I want this quantity to be. So this is the violation, or this is the separation that I'm going to see. This is an extra parameter normalization that I'm going to make sure that my W's are not too large. I don't want my vector W to be too large, and therefore I want to control its growth, and one way to control that growth is to put a multiplier here. Why do I want to put C in the denominator? Because later on I want to multiply this C over there. That's why I've just put them in the denominator. What kind of a loss function do I want here? The loss function that I want is a loss function which is shown here. So ideally I want this function to be greater than or equal to 0. W transpose X plus B must be greater than or equal to 0 whenever Ti is equal to 1. W transpose Xi plus B must be less than or equal to 0 whenever Ti is negative. So I want the quantity inside the bracket to be generally greater than or equal to 0. If it turns out to be less than 0, I want to put a penalty on it. I want to say that incurs a loss. If it is positive, I don't really care, right? So the function that I want to impose is this step function. Anytime I have positive, anytime the bracket inside, the quantity inside the bracket is positive, I don't want to impose any penalty. Anytime the quantity inside the bracket turns out to be negative, I just want to count an error. I want to be able to say that you give an error of -1 or give a penalty of 1 whenever things are negative. I don't really care how negative they are. Anytime it's negative, you give a penalty. Anytime it's positive, you give no penalty. This is the problem that I want to solve. That loss function should be this black function. But that black function is a step function. It's not going to give me a convex problem. It's not going to give me a very nice optimization problem to solve. So I can start making different kinds of approximations. And typically when you make these approximations, you find an upper bound. You put a loss which is larger than the loss that you want, become more conservative than being less conservative. So I want to be more conservative. I want to put a larger loss function. There are many choices possible. One is this blue line, and that blue line has basically an approximation which looks like what is that line? So the blue line can be written as 1 minus x positive part, which is the maximum of 1 minus x and 0. So when x is equal to 1, this becomes 0. For any larger values of x, this becomes negative, and you take the maximum of a negative number and 0, you get 0. For anything when x is equal to 0, you get 1. When x is negative, this quantity becomes greater than 1, and that quantity picks up. So this is the blue line, which turns out to be exactly this function, maximum of 1 minus x and 0. What about the red line? The red line corresponds to the logistic logs. So this is the log of 1 plus e to the power of minus x. So that's what the loss of x is, that, or the loss of x is that. So that one will give me, basically in the previous slide I'm going to show you, this corresponds to SVMs. This corresponds to logistic regression. And this yellow line, just by your guess, what would it correspond to? If I put that loss? Yeah, parabolic loss means what? If I put parabolic loss to this loss function plus 1/2 of W transpose W? What is the data analysis technique if I put a squared loss here? Linear regression. Not quite, because this is ridge here. So it's a ridge regression. This will give me the linear regression term plus a normalization that comes from W transpose W, you get a ridge regression term. So what is the point that I want to make out here is that all of these things are basically trying to attack the same thing. There are different ways of classifying. You can do logistics based classification. So blue, the hinge error function in support vector machine shown in blue, along with the error function for the logistical regression, and then also misclassification in black and squared error in green. So this is what it's calling green, but it looks yellow to me. So that one is the squared error. So if you're minimizing the squared error, you end up getting ridge regression. Here you'll get support vector machine. Here you get logistic regression. So I don't want you to think of support vector machines as something so dramatically different from regression. It's very similar. It's pretty close to it. You just put a different loss function. Later on, we'll see that there is another idea called support vector regression, which is slightly different from linear regression, and we'll get to that. Okay. Now what I want to do is go back here, and I want to solve. Where did it go? No. I want to solve this problem now. And this is the 1 minus x. So remember, see, this is exactly the same function, 1 minus x and 0. That's what the maximum function over there says. All right. So this is Ti, W transpose x, I minus b. This is the loss function that is sitting in here. And this is the loss function that I'm going to use in order to get to support vector machine. So what's happening over here? Let's think about this for a moment. If Ti times W transpose Xi plus B is greater than equal to 1, meaning I have classified that point correctly, then 1 minus this quantity is going to be negative. The maximum of a negative number in 0 will be 0, and you will not penalize it. If this quantity happens to be less than 1, meaning that I did not classify it correctly, then this will turn out to be positive. That positive number in 0 will be picked up, and you'll end up getting that quantity. All right? So that's the penalty, and I want to minimize WB. There are many ways of doing things. There is a way to reformulate it this way, whereas you introduce a new variable Ci for this maximum. You can write it as Ti W transpose Xi plus B is greater than or equal to 1 minus Ci. Ci must be greater than or equal to 0. There is a convex quadratic program here. You can do all kinds of things from there. What I want to do is write it slightly differently. It will set up things for something called first order optimization methods, which are the method of choice right now for solving very large scale problems. So let me motivate that for you and see how we can do things with that. So I want to solve the problem minimize 1/2 W transpose W plus C summation over I going from 1 through n, the maximum of 1 minus Ti W transpose Xi plus B and 0. Now I'm going to play a little bit of a trick. I'm saying that this is the minimum. This is the same thing, 1/2 of W transpose W. So far nothing has happened. For this one I'm going to put it inside. I'm going to say that I is going from 1 through n, and now let's try to understand what's going on over here. Maximum of Ui 1 minus Ti W transpose X plus B such that 0 is less than Ui is less than or equal to C. Let's think about what happened over here. My claim is that optimization problem is exactly the one over there. For every data point that I have, I've introduced a new, and in order to be consistent with what's going to happen later, let's call this alpha. So I'm maximizing over alpha. Alpha lies between 0 and C, and I'm maximizing alpha I times this product. So let's think about it for a moment. If this product is positive, what would I choose alpha to be? If this quantity, this number is positive, what would I choose alpha to be? C. Right? If this quantity is positive, I'll pick alpha equal to C. It's best for me to, since the derivative with respect to alpha of this quantity is this bracket, if the derivative is positive, I'll go and hit this value C. If on the other hand this quantity is negative, what will I choose my alpha to be? 0. So what is the optimal solution of this optimization problem? Not C. The optimal, sorry, not optimal solution, the optimum value of this optimization problem, regardless of what's going to happen. If this quantity is positive, the optimum value is going to be C times this quantity. If this quantity is negative, it will be 0 times this quantity, which is 0. Exactly that. C times the maximum of this quantity and 0. If the maximum here turns out to be this quantity, you will get C times that. If the maximum here turns out to be 0, you'll get C times 0, which is 0. Why did I do this business? It'll become clear in a moment. Now, this minimization is over W, that maximization is over alpha, right, of that. Let's try to see, let's write this both together. Minimum over W, maximum over alpha, 1/2 of W transpose W plus summation of I going from 1 through n of alpha I 1 minus Ti W transpose X plus B. And alpha lies between 0 and C. Each component of alpha lies between 0 and C. Everybody with me so far? All I did was I took these alphas outside. Okay. Now, this is a saddle point problem. It's a game. There are two players here. There's a minimization player and there's a maximization player. One wants to minimize this value, the other one wants to maximize this value. In some conditions, I can switch the order of the players. I can do the maximization after I do the minimization. Under what condition should that happen? I have to check this function. The guy who's minimizing, the function should be a convex function. So this is a convex function of W. Here it's a linear function of W, so the whole thing is convex in W. The one that is maximizing should have a concave function here. So this one doesn't depend on alpha, I don't care about it. This is a linear function in alpha, it's definitely concave. The other thing that I want to make sure is that the optimization problem will not go off to infinity. Alpha cannot go off to infinity because it's bounded to be lying between 0 and C. What about the W guy? Can it go off to infinity? Yes? Yes? No? Maybe? I tell my students maybe is the right answer. You never commit to anything, yes or no. But since you guys are much more experienced people, my claim is that W cannot go to infinity. How can I make sure that, what makes sure that W cannot go to infinity? I'm minimizing, remember? And I've got this guy sitting here. That's a quadratic function of W. It will never allow the W to go off to infinity. So the solution will be bounded, and so I'm allowed to switch the order. So I'm going to write this as maximum over 0 less than alpha I less than equal to C. The minimum over W, the same expression, 1/2 W transpose W plus, let's write this out a little bit separately, I going from 1 through n of alpha I Ti Xi, the whole thing transpose W plus, with a minus sign here, sorry, minus, plus summation of alpha I minus summation of alpha I Ti B, I going from 1 through n. So I've just collected together the terms. This one is alpha I Ti Xi transpose W, summation of alpha I is sitting over here. Then last one is alpha I Ti times B, which is sitting over there. And this sorry, I forgot. This optimization is over W and B. All right. Okay. So if I do the optimization with respect to W and B inside, I take the gradient and set it equal to 0. Take the gradient with respect to W. I'm just trying to solve this part. If I take I'll put it onto the other side. If I take the gradient with respect to W of this function and set it equal to 0, I will get W from here. I will get minus summation I going from 1 through n alpha I Ti Xi must be equal to 0. If I take the derivative with respect to B, I will get summation of alpha I Ti must be equal to 0. These are the two conditions that I get. If I take the value of that W and stick it back in there, you will work it out in your homework. I don't have boards to show the further. You'll end up getting basically that expression. Summation of alpha I Ti equal to 0, that's coming from right there. 0 must be less than alpha I must be less than C is coming from right here. You're maximizing that. And what about the leftover part? So summation alpha I is sitting there. Now from here, if you plug that back in, let's do that on this side. Where's my razor? Here. So I know that W is the summation of I going from 1 to n of alpha I Ti Xi. So if you look at 1/2 W transpose W minus summation of I going from 1 through n alpha I Ti Xi transpose W. If you plug that back in, you'll end up getting that this quantity is nothing but W transpose W, and this is 1/2 W, so this will turn out to be minus 1/2 W transpose W, which is equal to minus 1/2 I going from 1 through n of alpha I Ti xi transpose summation over j alpha j Tj xj. If you write it out in gory detail, that's the term that is sitting there. Alpha I alpha j Ti Tj xi transpose xj. That's the terms there, and that you end up getting as the calculation. So why did I go through this story? The reason I wanted to go through this story is because of this trick. To be able to show to you that this maximization has a very nice expression. And tomorrow, when we get into a little bit, when you're done with most of it, and I'm going to try to tell you how these problems are solved in practice nowadays, this trick will become useful again. So right now, it's just another way, and at the end of tomorrow, I'll give you a homework problem where you will do this on a different problem, so you'll get a little bit more experience. All right, so whether the problem is separable, whether the problem is not separable, basically, at the end of the day, what is the difference that happened? If the problem was separable, we just didn't have this. Everything else was the same. If the problem is not separable, you end up getting a cost C. How do you get that C? By cross-validation. So going back one more slide, the penalty C is chosen using cross-validation. So at the end of the story right now, where are we? If you give me a linear classifier, whether or not the data points are separated, I can figure out how to compute the best linear classifier. But linear classifiers are boring. They don't give me very good performance. So I want to be able to do this without going beyond linear classifiers, and that's where the story of kernels and things of that sort are going to come in. So if you think that the data is not linearly separable in X, then use a feature map. Lift this data point somewhere in higher dimensions. And in some dimension m much greater than m. What kind of a feature map would I use in this data? How would I construct a feature data point? Let's say that we're talking about images. So I have pixels. I have taken all my xi's and they were all pixel values. I made it into a large vector, which is just the pixel values. What kind of feature maps would I construct? How would I lift the problem? I want to decide whether this photograph belongs to Colin Powell or George Bush. So I want to be able to look at features. How would I think of constructing this feature map? This particular problem, let's say of images, what's a nice way to think about features? Distances, yes, but distance is already there between vectors, right? In some ways, can I do something else? What's that? If I want to recognize images, if you want to look at a person and say, that's my friend, in some hazy picture, what do you look at? Do you look at their cheeks? You of course look at their pixels, but are there particular regions that you look at? Eyes, nose. So you can look at you can stack up things which have to do by looking at their various features corresponding to the contours around their eyes, around their nose, around their forehead, what have you. There's a way of looking at a higher dimensional, you can get more information that is specific to that particular object, which is a face. You can look at correlations. If you think that there is a nose area, then you know that all of the pixels there should have some correlation. Maybe you can take products of those pixels, and that will become a feature. You can, for those of you who've done some amount of digital Fourier analysis, I can convert the image into a Fourier basis and look at what's happening there. I can do wavelet transforms that are more localized. All of these things are features. All of these things I can keep adding. Every time I keep adding this information, I'm increasing the dimension of the problem. I'm adding more to that vector. This is what I'm saying, that now my feature map lives in a space, capital M, which is much, much larger than little m. we will see in a moment, going back to what Raghu was mentioning, that there is another way of doing this which is actually a lot better. So now what we're going to do is, remember in the dual problem, only thing that matters is xi transpose xj. So instead of phi, now instead of the vector xi, I have some higher dimensional vector phi of x. So I simply replace that by phi of xi transpose phi of xj. Everything else works just as it is. I lift this problem and then I solve my SVM in this higher dimensional space. That will tell me what I'll get a new separator. B star I can compute as it is, and if I want a prediction at a new point, I take W star transpose phi x, which is going to be, I know by my calculation, alpha star I ti phi xi transpose phi x plus B. That's another way of doing everything in a higher dimension. But now I start thinking that really all that matters is this inner product. I don't really care about what the feature map was. Whatever be the feature map, there is something very wasteful happening. I have this little guy x, I lift it to a higher dimensional space because I think things are better over here. Then I take the inner product of those two vectors, which means it's basically one dimensional. I took this higher dimensional space and then reduced it to one dimensional because inner products reduce it into a scalar. So it appears somewhat that I'm doing too much work. And general principle, I mean, if in life and in sciences for sure, is be as lazy as you can. Don't always have to work the hardest, or at least wastefully just running around is useless. And that's what is happening over here. Phi has been, it's been lifted to some high space, then brought it down. Is there some way I can get around it? And that's the idea of kernels. So this is going to take a little bit of working, but we will get there. So we'll say a function k is called a kernel if and only if if you give me, it's a function of two variables, x and x prime, two vectors. You give me two vectors. I'm going to call a function of these two vectors, x and x prime, a kernel, if I can write that as phi x transpose phi x prime for some feature map phi, potentially with m being infinity. So far this is a tautology. It's completely useless. I said if I want a feature map, then I can do phi transpose, I can raise the vector x to some space, higher dimensional space, take the inner product, but that's precisely something that I wanted to avoid. So far nothing has happened, but there is a beautiful result called Mercer's theorem, which will come in a moment. So let's now take any set x of vectors. Take any n vectors, x1 through xn, call that set capital X. Define a matrix called the gram matrix of these vectors. And what is the gram matrix? The ijth element of this gram matrix is simply the function evaluated at the point xi and xj. Right? And why does this gram matrix make sense? Let me actually tell you why this gram matrix is an interesting object. My eraser is all on that side, so maybe I'll write it on this side. So suppose I've been given vectors x, which x1 up through xn. I define a matrix K in this form. Kij is just xi transpose xj. Forget about that little k function for the moment. It's just xi transpose xj. This is how I define my K matrix. So K is a matrix in R n times n data points. So this belongs to n times n. The ijth element is xi transpose xj. What can you say about this matrix K? Can I write this matrix in a nicer form somehow? So in order to write that in a nicer form, consider this matrix X, where these x1 through xn are sitting as columns. Then what is this matrix K? Yeah, close enough. It's not, if they were mean 0, they were covariance matrices. But what is the structure of this matrix? Can I write K in terms of X somehow? Yeah? So if Kij is Xi transpose Xj, can I write this K in terms of this X directly somehow? Somebody said the right answer, go ahead. X transpose X. X transpose is X1 transpose, Xn transpose. X is X1, Xn. And if you do this multiplication, you will see that the ijth element is exactly that. So this matrix, if I just give you the vectors x1 through xn and I define things this way, the Gram matrix K is nothing but X, capital X transpose capital X. What can I say about this matrix? What kind of a matrix is it? Definite, we don't know. Semi-definite, for sure. Right? So this matrix is positive semi-definite. All right. This quantity is actually a kernel. It is an inner product. So somehow I want to generalize this area. This X transpose Y. Suppose I define a function kxy equals X transpose Y. Suppose I define the function kxy to be X transpose Y, then for that X transpose Y, all of these properties are nicely there. If I give you any two vectors and I define this Gram matrix as Xi transpose Xj, then the corresponding matrix turns out to be positive semi-definite. So let's try to say that if I want something to be a kernel, then remove this and define this to be K Xi Xj. And insist, K is no longer this way, insist that this matrix is positive semi-definite. I don't have this structure anymore because this product is no longer X transpose Y, it's something else. But I only want to insist that I'm going to construct the matrix as I was constructing before by putting the ijth element to be the function evaluated at the vector I and vector j. I construct this matrix K and I want to insist that that is positive semi-definite. Suppose that's the only thing I have. Is it good enough? So I take any set of n vectors. N is also random. So take n to be anything. Take a set vex of vectors x1 through xn. Construct this Gram matrix and insist that it's positive semi-definite. If that happens, there is a very nice theorem called Mercer's theorem which says a kernel, a function kxx prime is a kernel if and only if for all possible choices of x, x1 through xn, the Gram matrix kx is positive semi-definite. As long as you check this positive semi-definiteness, it's going to be a kernel matrix, meaning that I would be able to find this phi that will work. Potentially this feature maps phi might be infinity. Still, it doesn't help me much because I've just rewritten it. It just told me that, okay, if I have a bunch of kernels that satisfy this inner product condition, life is good. It turns out that there is a recipe for constructing kernels. We will go to the next step and I'll tell you how the recipe for kernels work. But this gives me some way of saying I don't have to go to the feature maps. I can get away without feature maps, and that's the direction that I want to go in. I will get to this. Let me actually tell you this and then I'll go forward. So why do I care about kernels? Because remember this story that I was trying to build up, that I went from X to this higher dimensional space and then came down. Somehow directly going from this low dimensional space to my kernel should be computationally efficient rather than going to this thing and coming down. And that's the problem that I want to show you. So suppose you have a function which is kxx prime is X transpose X prime plus C squared. I haven't told you that this is a kernel. In a few slides I will show that this is a kernel. For now, believe that this is a kernel. Now, it's easy to check that this kxx prime can be written as phi x transpose phi x prime, where phi x has this structure. So x lives in Rm, and so the way to construct this product squared is going to be basically you take the constant c that will correspond to the c squared term that's going to come from this product. You take all the linear terms from x1 through xm that will correspond to the term 2 times c times x transpose x prime. So I put the square root 2 here and the c square root 2c here, square root 2c here. When you multiply them, you'll get 2c, and the corresponding x1 from this will multiply with x prime 1, x2 will multiply by x prime 2, and that will give you the linear term. In order to get the term that is coming from this squared, you'll have to take square root of 2 x1, x2, all the product terms all the way up through xm squared. So in order to compute kxx prime, what do I have to do? I have to compute this inner product x prime plus x prime. That takes order m work, which is the dimension of x. The squared is order 1, so it takes order m work. If I want to construct this feature vector, that requires me to construct this vector and then take its inner product. What is the length of this vector? It is m choose 2, m plus 2 choose 2. That is the length of this vector, and it might be a good exercise to figure out how to do this. Ages ago, when I was appearing for JEE, there used to be all of these kinds of questions that one has to figure out, that how do you get these combinations and permutations. So it might be worthwhile exercise to see how that happened, just to go back in time. That is of order m squared. So if you compute this quantity using the kernel, you get order m. If you first consider this feature vector and then bring it down, you do order m squared work. So if m is reasonably high, you're saving a lot by doing the kernel rather than by going to the feature vector. If, for example, the kernel was defined as x transpose x prime plus c to the power p, which is also a kernel, computing this still remains order m, because all I have to do is do this inner product. When I have a scalar, this is order 1 to change to the power p. But now working with the corresponding feature mapping will be order m to the power p. So as p becomes larger, the difference between doing kernels and versus feature maps is huge. So we love kernels because they are almost like inner products, they're almost like feature maps, but they can be done computationally much more efficiently. All right, so how do we construct kernels? So here's basically the story. Yeah, we have time. We can finish at the end of constructing kernels and then we'll go start again. So suppose let's consider these rules. So suppose I've been given 2 kernels to begin with, k1xx prime, k2xx prime. These are, suppose somebody tells you that these are kernels. A constant c is c greater than 0 is a constant, f is any function, q is a polynomial with non-negative coefficients, phi fx is a function going from x to Rm, k3 is another valid kernel, A is a symmetric positive semi-definite matrix, these are variables and so on. So let's see how these will play a role. So here's what happens. If you take a kernel and multiply by something which is non-negative, you get a new kernel. If this was a kernel and you multiply by c which is positive, you got a kernel. If this is a kernel and you put a function fx prime on this side and a function fx on the other side, you get a kernel. If you take a kernel and raise it to a polynomial, you get a kernel. And this is what we will use to prove. Let's stop right here. I want to use that property to prove that the quantity that we had was a kernel. So I claim to you that kxy defined to be x transpose y plus c to the power p is a kernel. How do I prove that? I'll start off with k1 xy to be equal to x transpose y. This is definitely a kernel. Why? Because this is straightforward and inner product. Now I will use that rule number 3. I claim that kxy is a polynomial Q of x transpose y plus c to the power p. So this to the power p is actually a polynomial, but what do I need that polynomial to do? Let's go back. Is a polynomial with non-negative coefficients. So in order for this to work out, for this to have non-negative coefficients, so q of x plus c to the power, q of x to be defined as x plus c to the power p. If I want this polynomial to have non-negative coefficients, what should happen to c? If I think of this as a polynomial in x and I define it to be x plus c to the power p, when will this polynomial have non-negative coefficients? As c is positive. As long as c is positive, this q of x will have non-negative coefficients. As long as c is greater than 0, actually greater than equal to 0. Yeah. So if you go back to that slide that was back there, it turned out that this is, I did not implicitly write it there, but I needed that c to be positive for this to be a kernel. If c is negative, this is no longer a kernel. If c is positive, this is a kernel, and implicitly I assume c is positive because I'm taking square root of 2c over here, and so implicitly I'm assuming that c is positive, but in order for it to be exactly true, that c has to be positive. So now we've used that rule and showed that the quantity that I was using was a kernel. Take the exponential of a kernel, you get a kernel. Take the summation of two kernels, you get a kernel. Take the product of two kernels, you get a kernel. You lift the variable first and then take the kernel, you get a kernel. X transpose AX prime is a kernel as long as A is positive semi-definite. If you have two subvectors, you take a kernel on one subvector, take a kernel on the second subvector, add them up, you get a kernel. Take the product of two things, you get a kernel. So there are lots of things that you can do. So what the mechanism for doing kernels is that you take a basic kernel and then you build things from there. Here's another story. Gaussian kernel, which is extremely useful, used all the time, is defined as that. K of x prime is the exponent of minus x prime squared divided by 2 sigma squared. This doesn't quite look like an inner product at all. But let's look at our rule. So we expand this. Exponent of this quantity is exponent of minus x transpose x over sigma squared, exponent of minus over 2 sigma squared, exponent of x transpose x prime over sigma squared, exponent of minus x prime squared x prime divided by 2 sigma squared. This quantity, just define it as some function of x, then this quantity is the same function of x prime. If you define this to be a function of x, this is nothing but the same function evaluated at x prime. What about the stuff in the middle? I know that x transpose x prime is a kernel. Multiplying it by a non-negative number 1 over sigma squared gives me a kernel. Taking the exponent of that kernel gives me a kernel, and therefore this entire thing is a kernel. Therefore this Gaussian kernel in fact is a kernel, and we end up getting that all of these things. One of the nice things about kernels is that you can define kernels on symbolic variables. You can define kernels of graphs, sets, strings, text documents, what have you. So if you take a fixed set and define the space consisting of all possible subsets of this set, so if A1 and A2 are two such subsets, then let the kernel of A1 and A2 to be 2 raised to the power the intersection of A1 intersection A2, where the modulus of A denotes the number of subsets in A. So you take the power set, so basically take the intersection of this and take the power set of that, you'll end up getting that quantity to be a kernel. This is a valid kernel because it can be shown to correspond to an inner product in a feature space. So we can easily now use SVMs to classify these sets. So you can, once you have a way of defining kernels, you can do SVMs on graphs, sets, strings, text document, what have you. Anything, as long as you can define a kernel. So we started from something which was linear separators on vectors to now going into linear separators of graphs, as long as I can define a kernel for it. Now the dual separation value of the dual value turns out to be, instead of whenever there was an inner product here between x transpose x, I replace it by a kernel. So the dual optimization problem will be sum of the alphas minus 1/2 alpha I alpha j ti tj, this kernel. Sum of the alphas is equal to 0. The optimum dual, given an optimal solution alpha star for this dual, you can construct the B star from any alpha star j which is positive, and again the same comment holds. You want to make sure that you take the averages in order to remove any normalization errors. Now if I want to look at how do I classify a new data point, remember whenever there is a kernel it corresponds to a feature map. So let's write it in terms of feature map. So it will be W transpose phi x plus B star, but now this quantity is nothing but alpha star I ti, the kernel xi x. So nowhere in the process of either solving this optimization problem or constructing the prediction do I ever need to create that feature map. All I need to do is be able to compute kernels, and so from there I can do now things on the nonlinear space. And here what has happened is, this is an example of synthetic data from two classes in 2 dimensions showing contours of y of x obtained by a support vector machine having Gaussian kernel function. Also shown are the decision boundaries, the margin boundaries, and the support vectors. So everything that is circled now is a support vector. So there are 2 Gaussian separators. So this point, this line, dark line here, is actually the separator between the 2 classes. These 2 classes are not linearly separable. They are not linearly separable, but in the Gaussian kernel space, they the data is linearly separable in the Gaussian kernel space, but not in the original space. Because of the curvilinear space, it's not able to get separated by linear, but it can do it in Gaussian kernels. So the last thing I want to show you is this little picture. Let's hope this works. So these are the data points. The points using a polynomial kernel, they can be linearly separated in 3D space. So what you're going to do is take these points. I'll run it again to be seeing what happens. It's a very, very simple story. Look at the video and then I'm going to go back and tell you exactly what is going on in this story. So the blues are below that line, the reds are above that line. And then when you project it back down, you get exactly the circle in between. Let me redo this so that you see. Hold on, let me stop this so you'll be able to see what's going on. Okay. So what's going on here is that you have these red dotted points that are outside and the blue dotted points that are inside. So you want to put a polynomial so that all the quantities inside will have small values of the polynomial and all the points that are outside will have a larger value of the polynomials. So if you do that, then all the points outside the circle get picked up, become very large. All the points that are inside the circle remain relatively small, and now you have a separator. And that's sort of the idea behind many of these stories. So I'm just going to show you once more and then we will stop here and then, whoops, what happened here? Oh, there we go. So those blue points over there will have small values of the polynomial. The red values have larger values. This is the polynomial that has lifted them. We never see that lifted space. In that lifted space we have a linear separator, but we never go and see that space because all of this happened in the kernel value. And that's effectively what I was telling you before. We went up into some space, did the linear separator, and then came back into normal space. But we can automatically do this without going through all of this drama. Okay, so we shall stop here today.